Hello, I'm Alexander Nutz. I'm holding a talk on separating map variables in a logic-based intermediate verification language. And this is joint work with Daniel Dietsch, Matthias Heitzmann, Jochen Hönicke, and Andreas Podelsky. So what I'm presenting is a program transformation where we transform a program P to a program P prime such that P prime is easier to verify but still has essentially the same behavior, meaning that if we can use the verification result from P prime also for P. So in particular, P is a program that has maps and is in a logics-based intermediate verification language such as Boogie or constraint horn clauses. So these intermediate verification languages are a very common intermediate step when writing a software model checker. In particular, our software model checker Ultimate Automizer uses it, but also many others. Now, the idea of the transformation is that we have map variables. Now, as a side note, when I say maps, I could also say SMT style arrays or functional arrays. They are basically the common way to represent, for example, arrays in C in an intermediate verification language, but they have certain subtle differences. So now the idea of the transformation is to split heavily used maps into independent parts and thereby make the program easier to verify. Now, to zoom in on that a little bit, a common pattern in pretty much any program with maps is a statement sequence like this. So we have a bunch of update statements. For example, here A at index I1 is updated to value x1 and so on. And then at some point we read from that map A at an index j. So what we don't know is whether these indices, like which of these writes are even relevant for this read, because we need to know which of the indices alias and which don't, essentially. So in terms of SMT, we get a term like this when we want to know the value for x, so for y, sorry. So y would be equal to a, and then we store at I1 this x1, at I2 this x2, and so on, and then we read at j. So this is called a stored chain, and it has the length n. And in order to retrieve the value at j of this updated map, we need to know if j equals in at time of the read, and if it doesn't equal that, we need to know if it equals in minus 1, and so on. And this of course induces a lot of decisions on the underlying solver, because each of these equalities is essentially an atom that, among other things, will have to be set and possibly backtracked upon by the set solver, which can of course become expensive. So and this is kind of a well-known bottleneck in manipulating programs and their verification. So our approach to this problem is to compute beforehand independence information between reads and writes. So we try to find out, is it even possible that A is written by this first statement at I1 in a way such that this value even reaches this read. So there are various reasons why this couldn't be the case. So for example, I1 and j can never be the same, then there's independence trivially, but it could also be the case that some assignment along the way always overwrites that x1 value, so then it would also not influence. So let's, for example, assume that only the first and the third statement can influence this map read statement. Well, in that case, we could split up our map variable a into a few different copies, and we could say that, okay, now if we read from a1 to get this in this read here, then only the writes at the first and the third write are relevant, and thus only they need to write to the map a1, and the other writes can go to a2 and a3, and thus they're trivially independent, and the stored chain that we're looking at also becomes much shorter, which means fewer decisions for the solver. Now that would be nice. So to give an example on a full program, which is still rather small for the sake of presentation. For example, we could have this program with a memory array, which essentially stores values as normal. It could represent a heap or something, and a valid array, which essentially is does allocation management. So valid will be set to true on all indices where mem is considered allocated, and we're only allowed to use allocated space as usual. So in our program we would allocate two pointers p and q, and then we would set mem at both of those pointers to 0, and then non-deterministically increase at p and decrease at q. Now it's clear that this program is correct, namely for the specification saying that at p we have only increased and at q we have only decreased, but with the fine print that this is only the case if p and q are actually different, because if they alias, basically anything can happen at that memory location. Then the same location is increased and decreased, and both assertions can be violated. So now, so it's crucial for a verification to understand that p and q are distinct in any case, and this is done by, in our case, by using this specification of malloc. So it's often practical to use a specification instead of a practical implementation, and here we have this basic specification of malloc, which essentially makes sure, using the valid array, that no index is allocated twice. So now when we know that, then we know that p and q are independent, and then we can transform the program into one that is simpler to analyze. And because mem1 and mem has been split into mem1 and mem2, and then the stored chains we have to look at here, which can be long, of course, because the while can have been unrolled an arbitrary number of times depending on our verification strategy. Then we have to consider stored chains, which are much simpler, since we don't have to consider updates to q when we're analyzing this read on p. Okay, so this is what our program transformation will achieve. Now let's look at how much easier to verify this transformed program is. So this is essentially, this x-axis represents variance of our transformed program, namely the 2 is the one we saw. It has 2 pointer variables. Now 4 has 4 pointer variables, and so on, but it's basically the same program, right? So again, we have to reason, in each of those we have to reason about independence information. And so what we can see is that on the left hand side program, scaled up, that we saw earlier, our software model checker, Ultimate Automizer, times out starting on 10 variables for a timeout of 1500 seconds. And yeah, after that we can't verify anything. However, on the transform program, which is represented by these boxes, the verification effort is essentially zero. Well, not zero, sorry, but essentially constant. Now, of course, we have to buy this with something, which is the static analysis cost, which is represented by the difference between the box and the circle, which goes up, but much, much slower than the cost of analyzing the original program. Okay, so now coming into the more technical part of my talk. So this is an overview of what I'm going to present. First, I'm going to define an independence property between reads and writes called last writes. And then I'm going to show how we compute an over-approximation of this property. And then I'm going to show how our transformation uses this information. Now, the last writes relation relates reads, writes, and reads to each other, as we can see. So, for example, this write with label L and this read with label L prime are related by last writes if in our program there is an execution which first visits statement L and then label L prime, and such that the value that is written by our statement at L is actually read by our statement at L prime. So now, for sake of simplicity, we're assuming that no value is written by two different statements. That's what this timestamp is suggesting. And yeah, and so essentially this definition means that when we visit our read statement at L, oh, I'm sorry, this has been exchanged. So this is the write statement. So this should be here on the side. So when we visit our read statement y equals bj, then the last write to j, to b at position j, must have come from our write statement ai at position a of our write to map a at position I. So now you might wonder why these maps aren't identical, so why a and b? Well, the reason is we can assign between maps. So just that we have written to a doesn't mean that the value can't reach map b. This is a peculiarity of our logics-based representation. Okay. So now the question is, how do we compute our relation? Now, in general, this of course involves, among other things, reachability and will be undecidable for most classes of programs that we are interested in. So what we do is we compute an over-approximation of the last writes relation. So how do we do that? We will go in 3 steps, namely we instrument the program with history map variables, as we call them. They essentially store, each of these variables stores a history of when a given map at a given index was last written, namely by the statement with which label. And then we run a static analysis, which gives us information about these history map variables. And from this static analysis result, we can extract our over-approximated relation. Now, in the first step, we have to instrument our program with these history map variables. So intuitively, we introduce a variable for every map A. We introduce a variable A last writes, such that A last writes at each point in time in the program execution of the instrumented program stores when A at that given index was last written. So, and it stores the label of the writing statement. So for example, for instrumentation, we transform a write to A at index I into a write into the same statement again, and also a write to our A last writes at the same index I, but there we store the label of the writing statement, namely L. So another case is when we assign maps, then we just have to assign the last writes maps along with the original maps. And also interesting, when we havoc, then we have to set the last writes to a constant array, which is false, meaning the bottom representing the fact that at each position there was no write so far and A is uninitialized. So now the question is, which domain can we use in order to infer this information? While in principle we can plug in any static analysis, it of course has to be efficient and strong enough for our purposes. So in another paper we're presenting analysis which has these properties, and I'm going to present it in just one slide here. So the basic idea is that our abstract domain is a product of domain of equalities, of a domain of disequalities, and of weak equivalences. Now, a weak equivalence essentially states that two maps A and B are equal on all their indices, but they except for a set of indices which is given by this predicate Q. So as a formula, the meaning of this relation is that for all indices Q, A and B are equal at Q, or this predicate for Q holds. Now, this predicate is again a predicate in our domain which stores equalities and disequalities. So yeah, so we're presenting the domain in this paper. So when we have a result from that domain, we can easily, so it can be any approximation of our last writes relation, but if we have that, we can easily construct an equivalence relation over the write statements in our program by relating all the write statements that may influence the same read, and then computing the transitive closure, which will give us an equivalence relation. So what we get is essentially a bunch of write blocks. So a partition of all the writes which which aren't necessarily independent according to a property. So this partition we can use to define our program transformation. Our program transformation will take for each array map update statement, it will look for the write block that the array update is in and use a fresh map variable that's associated with that write block. And each write block gets its own map variable, AW. Now for a read, then we again look for the write block that's associated with influencing that read and read from the corresponding variable. And for example, for a map update, we have to, for a map assignment, like assigning a whole map, not just one value, we have to essentially assign right block by right block. Now, again, this you already saw this graphic. I'm just going to go over it once more in this with this bit more context. So Automizer is the model checker we ran on, and in the red crosses, we have the runtimes for the original programs, and with the boxes we have the runtime on the transformed programs. Again, the same program from our example slide scaled up by the variables, and and for the circles we have the addition of the runtime of the whole program transformation that of course we should factor in for fairness, and the static analysis that was needed for it. The static analysis being the main part of that runtime. Yeah, and so as you can see, we can solve many more programs that way. Now to conclude, we've presented a program transformation for splitting map variables in order to make the program easier to verify. For that, we've introduced this last writes property, and we have seen on a proof of concept example that this indeed alleviates this SMT solver bottleneck that I talked about during the introduction. So future work is certainly to apply this technique to more like a wider range of experiments, like for example C programs from SVComp, but we're also looking for further applications, both for the map equality domain and also the splitting. Okay, here are the references, and thanks for listening.